Okay, good morning, ladies and gentlemen. It's a real pleasure to have with me today Professor Debra Fischer. She's a famous planet hunter, and she's a professor of astronomy at Yale University. Her research is mostly centered in detecting and characterizing extrasolar planets, or exoplanets, planets orbiting around other stars. Right. She discovered since 1997 150 exoplanets. So that's a good rate because we know 800 of them right now. So that's my first question as an astronomer. That's a question I always ask to my colleagues, in fact, is right. How did you become an astronomer? It's such a very specific work and job.
Right. I guess I was really interested in the way that the world worked, the way that the physics worked. And so I was interested in mathematics and physics, and it's really when I took my first astronomy class that I said, wow, imagine being able to study this. But I think the sort of aha moment, the real turning point came. I was studying physics at San Francisco State, working on my master's in physics, and I was a member of the Astronomical Society of the Pacific, and they had this online gift store, or I think at the time it was actually over in the Sunset. And I would frequent, turning the pages, just so excited about all that stuff. And so one day I ordered these prints, which came from the Palomar Sky Survey. And the prints were taken of the same part of the sky, but with 3 different band passes. So a visible band, the visible filter, a blue filter, and a red filter. And you could lay these down, and you could find little points which matched on all of them. But the universe, the galaxy, looked so different in each of these different wavelength bands. And it was sort of that realization that we see this tiny part of the electromagnetic spectrum, and the realization that we live on this tiny little speck of a planet in such a grand, galaxy, which is just one of billions in the universe. And the idea that also in time, we occupy this tiny moment in time, that suddenly I began to see physics and think about physics and mathematics in a completely different way, in a way that would sort of embrace everything with the insignificant exception of the Earth.
So that was your
and that was really it. Was just this, seeing firsthand. Oh my God, there's so much out there, and wanting to know more about it.
So the universe is vast, as you say. There is billions of galaxies around us. So right. Why did you decide to study exoplanets? Such a narrow field.
Right. Well, I was actually in the PhD program at UC Santa Cruz. And as I said, I had been at San Francisco State University working on my master's in physics, which is where Jeff Marcy and Paul Butler were. Paul Butler and I were taking classes together, and Jeff Marcy was a new young professor there. And so just as I was finishing up, the first exoplanet was discovered. And that was in 1995. And I had been doing work on spectroscopy anyway, which is the technique that we use employs spectroscopy. And so it was just an unbelievable moment in time, and a very lucky, absolutely lucky moment to just be sort of right place, right time, right area, and so lucky that, one day I had been to a conference. It was one of the Cool Stars meetings, and, I was sitting in the back of the plane, wedged in the middle row between 2 big guys, and then, here comes back from first class, Jeff Marcy, walks back and says, so, we're wondering if you'd like to join our team. And I just, jumped on top of the guys. Yes, I'll do anything. So it was luck, I think, and it was just so exciting.
And patient.
Yeah.
And Jeff Marcy.
Yeah, that's right.
All together. I think it was a good chemistry.
That's right.
So could you explain to us how you search for exoplanets specifically? Describe briefly the technique you have been using for years.
Right. Well, what we wish we could do is go up and take a picture of a star like those Palomar Sky Survey images and see the little planet sitting next to it. But we're going to have to wait for Franck, actually, to get those kind of images. So instead, we employ the laws of physics. We know that if a planet is orbiting a star, it's going to tug the star around a common center of mass. And since we can't see the planet, we're actually watching the star coming toward us and going away from us. Sometimes it's called the wobble technique. But it's really, we're looking at a spectrum of the star, and in the atmosphere of the star, there are molecules and atoms that absorb the light coming out and leave dark lines, okay, where a beautiful rainbow spectrum should be. And those lines wobble back and forth because of the Doppler effect. So we measure that, and I say that as if, it's easy and we're measuring this big swing, but the precision with which we measure this wobble is 1/10,000th of a pixel. Okay, so it's a quite intense software modeling effort.
So what's the limitation of this technique, basically? What do we know only?
Right.
We say only 800 exoplanets.
Right. So the limitation is that it comes down to stability, and it's actually something that my team at Yale is working on very hard right now. But again, if you think again about a pixel, right, on a CCD detector, and this is made up of a substrate of silicon atoms. What I'm saying is that one of these absorption lines spans 3 or 4 pixels on a CCD detector. And I said before, we measure the shift of this line to 1/1000th of a pixel shift. That corresponds to something like 100 silicon atoms. Okay, and that back and forth shift occurs at some arbitrarily long period, whatever the orbital period of the planet is. That's what the time that we have to keep everything stable and have it walk back and forth. So how we've done as well as we have is still, it boggles my mind. But it's going to come down to stability of the instrument, stability of our wavelength calibrator, the way that we couple the light into the spectrograph. We're in the process of tearing everything apart right now. And we have something called a diagnostic facility at Yale, where we're really trying to find out the impact of every little thing on the radial velocity precision.
So it's basically building an instrument specifically for
I
detecting
think so, right? In the early days, we had to share the instruments with other astronomers.
We don't like to share, right?
I know, we do not like to share, exactly. We missed that lesson in kindergarten. Because other people come and they mess things up, they move things around. And that is just, that is really the enemy of precision, the kind of stability that we need. So we're in the process of figuring out how to build special purpose instruments.
And all these instruments are on ground-based telescopes. Could you tell us what kind of ground-based telescope you have been using?
Right. We use everything from the largest telescope in the world, the Keck telescope, all the way down to some of the smallest telescopes. The Keck telescope, which is not seen here, I guess, but is a 10-meter telescope on the top of Mauna Kea. And we used, of course, for years the Lick Observatory telescope, the 3-meter Shane telescope, which is shown here. And I have a telescope that I use in Chile, which is just a 1.5-meter telescope. So the diameter is half the diameter of the 3-meter telescope. And there I'm looking specifically at Alpha Centauri A and B, targeting them 200 nights a year to try and beat down our single measurement precision and find planets there.
And why Alpha Centauri? Could you tell us
because
why it's important?
It's the closest star system to the sun, just 4 light years away. So if you imagine, someday traveling out into the galaxy, and I'm sure that if we survive, that we will be there at some point, where we're actually going out or sending small space probes to investigate, and you're going to go to the closest place first. It's the chance where if you were trying to have a communication, you could, the time lag wouldn't be so bad at 4 years.
Okay, so our galaxy contains like 300 billion of stars or something like this. So how do you how you choose your targets?
Right.
What criteria do you use? Because there's so many stars.
Right. And since there are so many stars to choose from, we basically choose the brightest stars. For the technique that I've described, the velocity technique, we need photons. We need a high signal to noise, and that means choosing stars that are bright and therefore relatively close.
Are they stars we can see?
They're not that bright. I mean, some of them are, right? Alpha Centauri is blazingly bright in the sky in the southern hemisphere. It's a 0th magnitude star, Alpha Cent A. But the stars, the stars that we're looking at go all the way to 6th magnitude, which is sort of the boundary of, where you really can't see it anymore, certainly not in the city, and fainter. So we do need telescopes to collect those photons.
So Just to go back to your career, what was your first major discovery? Did you have this kind of eureka moment that we have sometimes in science?
Yeah, absolutely. And it came with the Upsilon Andromeda system, which was the first multiple planet system that we had found. And I was a new postdoc then, working with Jeff and Paul. And my assignment was to actually mathematically model the data that we've been getting. I'd been driving like a mad woman, up Lick Observatory Road, every night at 4 or every afternoon at 4 o'clock, so I could get there just as the star was setting and get the image of it in the spectra and analyze it. And we were collecting data, and we knew we were really close. Paul and Jeff had found a planet orbiting in just 4 days around the star. And we saw this long trend in addition, which indicated that there was a second planet with a period of maybe 2 years. So that's what I was racing up and down the road to get, that second planet.
Did you get a speeding ticket for that?
I didn't get a speeding ticket, but I made a lot of enemies on the road. Yeah. And so, so when I modeled it, I was failing to get a good model. And so I subtracted the fit that I had and to look at the noise that was left behind. And the noise that was left behind went just like that. It was a third planet. And so to see this, 3 sort of Jupiter-like planets packed into a system like that was incredible. And to me, it was, walking across the campus to Jeff's office, looking at this model and realizing, wow, planet formation must be a robust process. And at the same time, we'd been hearing biologists say, wherever there's water, there's life. And, and now we're finding that, planets form in abundance, and just this sense that there was going to be a turning point for SETI, for finding life elsewhere, and that it was just amazing.
So Giordano Bruno was right. There is planets everywhere.
Yes, that's right.
So today, the Kepler mission is one of the major missions to search for exoplanets.
Right.
Could you explain to us what Kepler is about and how it's going to change the field?
Sure. So the Kepler mission, of course, goes up and it stares at a part of the sky which was carefully selected by the project scientists so that it's a little bit out of the plane of the galaxy. There's a field of 3 million stars, and from those 3 million stars, they've culled 150,000 that they're following very closely as their normal sort of main sequence adult stars, still burning hydrogen. And they're following those stars, staring sort of unblinkingly at the field, and measuring the brightness of all 155,000. And when a planet passes across the disk of the star, it's going to block out some of the starlight.
Like the transit of Venus?
Exactly, like the transit of Venus. I was in Hawaii for that. And so, you'll see a slight diminution in the starlight for the few hours that it takes the planet to pass in front of the star. And so that technique has been a watershed. We struggled, right, in the early days. Every planet was a press release, a paper. Now we're packaging them sort of, 5 or 10 at a time. Can't be bothered to write up one planet. And we struggled, and we've gotten, over 700 planets now with the Doppler technique. Then Kepler came along, and in just, since 2009, since it was launched, has, laid out this incredible, rich, harvest of more than 2,000 planets that have been, we call them planet candidates, but...
I was about to ask you that.
Right.
Why Kepler called the planet candidates, and why do you call them planets?
Yeah, so we call them planets because we think we confirm the mass. I mean, we measure the most of the orbit, except for the inclination of the orbit, and therefore we can determine from the laws of gravity what the mass of the object is. We don't see the size of the object. So what the Kepler mission sees is the size of the object. But how do you say if it's a planet, for example, or if it's just a low-mass star? Because it turns out that a low-mass M-dwarf is just about the same size as a Jupiter-mass planet. So there's a little ambiguity, although you can get information from the orbital period timing and things like that. That have led people to be cautious and call them planet candidates. And I think we're approaching a turning point where there's been enough follow-up that we're finding that something like 90-95% of these planet candidates turn out to be planets, okay, for the stars that are accessible, amenable to other techniques. And so I feel pretty comfortable in a statistical sense thinking of these as bona fide planets.
So that means that in a few years we're going to know 4,000, 7,000 exoplanets when Kepler will be done with the survey?
Exactly. Kepler has, fortunately, in the wisdom of the senior review, has an extended lifetime and will continue as long as possible, and for a few more years anyway. So we'll continue to see more planets come out that are wider and wider separations from their stars.
So you started your career with 1 or 2 planets.
Yeah.
And you're going to end your career with millions of exoplanets.
Hundreds, thousands, yeah.
So what's the future of, how do you envision the future of the field?
Yeah, so, we're always, you don't want to just keep doing what you've been doing. We'd like to do new things. And so as I said, in my instrument lab at Yale, we're working very hard to push down our precision so that instead of measuring shifts that, walk across 100 silicon atoms, we want to measure shifts that walk across 10 silicon atoms with periodicities of a year or more. Okay, and if we can do that, we will be able to detect an Earth at an Earth mass planet at a distance.
Is that your holy grail?
That's the holy grail. Finding a lot of planets that are similar to Earth in mass and at a distance from their star where liquid water can exist. If you look at the book Rare Earth, where they list all of these criteria why life must be rare, we can boil that down to actually 2 factors. If you have a planet that has the right mass and it's at the right distance from its host star, it's almost certainly going to have an atmosphere. It's likely to have plate tectonics, and I think it's probably extremely likely to have a life on it.
So when we're going to see this, when we're going to detect this Earth-like planet, what are we going to do after?
Yeah, that forward prediction is always hard, and I caution people that in 1993 there was a meeting astronomers were at, and people were saying, and there was a lot of rumbling because people knew that, hey, Jeff Marcy and Paul Butler have been at this a long time, Michel Mayor and Didier Queloz, and nothing's turned up. Maybe we're the only planet. Okay, I mean, that's what the astronomers and physicists were saying. How about that? Maybe we're the only ones. They've been looking. They haven't found anything. We're it. And so once we discovered one, we suddenly had this realization that the gas giant planets weren't all going to be out, at 5 AU orbits. The universe and the planetary architectures were so much different than we imagined just based on our solar system. So my feeling is that, once we do, and no one knew in 1993, would it be another year, 2 years, 20 years? But once that happened and that first planet was detected, all of a sudden we knew exactly what to do. And we started just, digging down that hole. And so I think, once evidence for life is found somewhere else, there's going to be an aha moment that's going to change the way that we look and the way that we think about the problem. And it's no longer going to be, we found the other civilization, but, wow, now we have 700 examples of other worlds that have signs of chemical disequilibrium in their atmosphere, something that indicates that there's some kind of a process taking place there that we would call life.
So this is going to be a universal aha moment.
Yes.
It's going to change the way we see ourselves in the place.
It will definitely change the way we see ourselves, yeah.
Okay, so we're going to open the floor for questions for the audience. So we don't see you, so I hope you're going to make sure that we're going to see. Any questions? Yes, you got one of them.
Andy.
I'd like to find out, I know you've been talking a lot about the fact that there are multiple planets around many stars,
Right.
and that it just takes time as we get further and further away from the star to be able to detect some of these more distant members.
Right.
So give us a sort of picture of what you're seeing these days in terms of multiple planets, star systems. Are there a lot more? Are you encouraged? Are there planets further and further out as time goes by?
Right. So that's a great question, and in some sense it's how do these other systems compare to our solar system as well, which of course is an example of a multi-planet system. What we're seeing, and this comes from the Kepler data, from the statistics of the Kepler data, is that The low-mass planets are preferentially found around cooler stars. So another way of saying that is that the gas giant planets, at least the close-in ones, are very rarely found around the most common types of stars, the low-mass stars. But the rocky planets, which I would characterize as anything from a couple of Earth radii to 4 Earth radii in size, so that's something like, well, we don't have an analogous planet in our solar system, so a couple of Earth radii to a Neptune in size. Those planets are common. Kepler is seeing them around at least 25% of the K and M dwarf stars, and the vast majority of those seem to be in multi-planet systems. So for the super Earths, the Earths, the rocky planets, there's enough safe space in the gravitational sense that I think those are going to be the rule and not the exception.
One more question here.
Talking about your high precision observations of Alpha Centauri, can we place a limit on the size of a planet that might still match the data that you've got at the moment?
Right.
Can you place an upper limit on the size of a planet there?
Right, we can, and also the Geneva team is, of course, in the southern hemisphere on an adjacent peak. We like to spy on them sometimes and hope it's cloudy over there. And they're looking at Alpha Cent, and we go to conferences where we kind of walk in and we're both nervous. Have they found anything yet? We've ruled out any kind of gas giant planets. We've ruled out Neptunes. One of the, you could call it a blessing and a curse, but of course this is a binary system. And so it turns out that any planets that exist around either star, okay, and we're not thinking about circumbinary planets which could exist, but we wouldn't be able to detect with our technique. So any dynamically stable planets have to be within 1 or 2 AU of the star. Once they get beyond that, they're disrupted, gravitationally disrupted by the other star. So that means we're able to actually push things down to about a Neptune mass planet around either star. But that still leaves a lot of space for Earths and super Earths. And I don't think either of our techniques are quite there yet in terms of the precision that we need. So.
In the meantime, I have one very simple question.
Yeah.
How do we name exoplanets?
Well, we wanted to, in the beginning, of course, name them, Planet Google, Planet Pepsi, help bring in money for our research. But I think we restrained ourselves pretty nicely, with a couple of exceptions. One of them being the Upsilon and Andromeda planets, which a class of 4th graders named Dinky, Tupiter, and Forpiter. The planets are named by the International Astronomical Union, the IAU, with a very boring convention. Since binary stars are, 16 sig capital A and 16 sig capital B, then the IAU gave the planets lowercase designations, and they reserved A always for the stars, so the planets could never be little a. So it becomes like the Dr. Seuss story of, the cat in the hat with little cat A, B, and C, and so we name them in the order that we find them, which leads to an alphabet soup, really, for the multi-planet systems, because often we'll find the big one that's further out, and then, by the time we find the little one close in, it's actually E, component E. So we find B, C, D, E, F, and they're jumping all around, but yeah.
So that means that in a few years, when I will be looking at the skies and I want to be romantic, I will tell my girlfriend, boyfriend, husband, this is Alpha A and this is Alpha B.
Right.
It's not going to be very romantic.
It's not very romantic,
Maybe
exactly.
we need to change that.
That I agree, actually, I agree.
One question.
I was hoping that you could say a few words about planet hunters and how ordinary people can participate in finding planets.
Yeah, thanks for that opening. So along with the founders of Galaxy Zoo, Chris Lintott at Oxford University and his crack team who are amazing, we set up a website called planethunters.org? I can't remember, I'm on the spot. Where we are actually serving up the Kepler light curves to the public. And we tried to put them in a very, attractive format. We kind of tested with high school students who are like, that is boring to look at. I don't want to, And so we came up with a design where they said, oh, that's kind of cool looking, and they were intrigued. And we also, spun it down so that when you go to the site and you're shown a light curve, you just ask 3 simple questions. Is it variable? Do you see wild variations in the sort of baseline brightness of the star, which can happen because of spots and pulsations and other things? And then do you see a transit? And we described that that's going to typically be sort of a little square, dip in the brightness. And if so, can you mark it? And then we have software that extracts those markings out and weights the probability based on, so it gets complicated. We actually inject synthetic fake planets into our data. Okay, and so we have the answer in the back of the book. And if the users find those synthetic fake transits, then we know what their grade should be in terms of flagging them. So we have a weighted extraction process for finding planets. And the people, the public, have actually found something like, we work closely, of course, with your team, with the Kepler team on this. We never, we wanted it to be complementary always. And so they found many of the Kepler candidates that your software that you wrote, John, has found. But then we found a few other examples as well, including one that we're working on right now, which is a planet orbiting a binary star system. So the ability of people to see these things, especially in complicated light curves, has really been unbelievable. And I talk to the Kepler team and say, and they're like, yeah, but you don't understand. I spend months staring at these light curves. But if you look at the total amount of time, right, that there's something like 40 or 50,000 users now on the site have contributed, it is 24/7, okay? It's like you sit down 24/7, you don't take a break, you don't sleep for 200 years, okay? That's the amount of time that collectively they've put into reviewing the Kepler light curves. And so they're finding things that are quite, unusual. So we're really excited about that.
So if you want to look for planets,
yeah,
you need to go on
planethunter.org. Right.
So I have one final question. What kind of recommendation will you give to a young person who wants to become an astronomer and specifically want to work in your field?
Right. So I would say, study mathematics and physics and be really broad. Study geology and biology because there are a lot of well-traveled roads, and what you want to do, I think, as a young person, is go off the beaten path. And to do that, having a broad education really makes a big difference. Also, computer programming. What's happening to the students now? They are coming to college without any. There seemed to be like a little blip where we all went through, and learned programming, and now it's. So computer programming, we can't do anything without that.
Computers are important. They help us to think.
Yeah.
Okay, let's stop this interview. Thank you very much.
Thank you.
Thanks for coming. You're going to be here for the entire
That's right,
day,
for the rest
so
of the day.
you can
Yep.
talk to her. Thank you.
Pleasure.
Again.
Yep. Thanks.